Hello, Matt here from chemistrystudent.com. In this video, we're going to look at clock reactions and specifically the iodine clock experiment. We're going to talk about what clock reactions are, how they can be used to measure initial rates of reactions, and go through the iodine clock experiment in detail. Rates of reaction, orders, and rate equations have been covered in separate videos. Check the links in the description below. Before we talk in detail about clock reactions, it is essential you are comfortable with what we mean by a rate of reaction. If unsure, please check out the videos just mentioned. As a quick outline for this video, however, rates of reactions describe how quickly reactions are occurring. They can be measured in terms of the speed at which reactant concentration decreases or the speed at which product concentration increases, given the units moles per decimeter cubed per second. Quick recap done, let's go. The concentration of reactants can impact the rate of a reaction. As the concentration of reactants decreases during a reaction, the rate of the reaction will usually decrease as a result. This kind of makes sense. The fewer reactant particles there are, the slower the reaction can happen. This does pose a bit of a problem, however, if we want to measure the rate of a reaction, as the rate is constantly changing as the reaction proceeds. We can wait until the reaction is completely finished and measure the rate as an average of how long it took for all the reactants to react. However, the average rate we calculate will be very different to the rate at the very start of the reaction, when the concentrations of reactants were at their highest. To help get around this and measure the rate as close to the start of the reaction as possible, we need a way of being able to know when only a small amount of the reactants have reacted way before their concentrations change significantly or they are all used up. Clock reactions are one way we can do this. In a clock reaction, a colour change occurs when only a small proportion of the starting reactants have reacted. If we time how long it takes for the colour change to occur, we can determine the starting or initial rate of the reaction. It's really important to note here that in a clock reaction, the reaction hasn't finished when the colour change occurs, and the reactants haven't all been used up at this point. It's just that a certain amount of product has been formed that triggers the colour change. If we want to measure only the initial rate of a reaction, it's key that when the colour change occurs, the concentration of reactants has changed only a tiny bit compared to their starting concentrations, as this means the rate is minimally affected by such a small change in reactant concentration, and therefore the reaction is still happening at pretty much its initial rate when the colour change occurs. This is the trick to a clock reaction, and depending on the type of reaction being studied, a second reaction is usually used to help control when the colour change occurs, enabling us to easily time how long it takes to form a specific amount of product. And from this, we can calculate the rate of the reaction, change in concentration divided by change in time. A common example of a clock reaction at this level is the iodine clock experiment, or Harcourt-Esson experiment. It's used to measure the initial rate of reaction between iodide ions and hydrogen peroxide. Potassium iodide is often used as a source of iodide ions, as it dissolves in water, releasing them. Iodide ions and hydrogen peroxide react together to form iodine molecules, I2, and water. Iodine molecules turn starch indicator a dark blue-black colour, meaning if the reaction is carried out with starch indicator in the reaction mixture, as soon as the reactants react and iodine gets formed, the colour of the mixture changes from colourless to dark blue-black. This is great, as we can know that reaction is happening and product is being formed as the colour changes. However, it only takes a tiny, tiny amount of iodine to change the colour of starch indicator, meaning the colour of the solution changes pretty much instantly when the iodide ions and hydrogen peroxide start to react. This makes it virtually impossible to measure the initial rate of the reaction, as the colour change happens too quickly to measure, and we don't know exactly how much product has been formed at this point anyway. To get around this, a small quantity of thiosulfate ions are added to the reaction mixture, alongside the starch indicator. This is because thiosulfate ions react with iodine molecules to form iodide ions. Now, as soon as iodide ions and hydrogen peroxide molecules react together and iodine molecules form, the iodine molecules in the mixture will instantly react with the thiosulfate ions present, forming iodide ions. This means the starch indicator doesn't get a chance to change colour. The solution will only change colour when all the thiosulfate ions present have reacted. As soon as that point occurs, any iodine molecules now formed from the main reaction between iodide ions and hydrogen peroxide remain in the solution, and bang, the starch indicator turns a dark blue-black colour. If we know the moles of thiosulfate ions added to the reaction mixture, the moles of iodine that must have been produced before the colour change occurred can be determined, and combined with the time taken for this colour change to happen, the initial rate of reaction can be calculated. One small thing to note here is that the molar ratio of thiosulfate ions to iodine molecules is 2:1. Meaning the moles of iodine produced before the colour change happens is half the moles of thiosulfate ions added at the start. The moles of thiosulfate ions present at the start should be very small compared to the moles of hydrogen peroxide and iodide ions. This makes sure that only a small percentage of reactants are used up before the colour change occurs, meaning, as we outlined earlier, the initial rate of reaction is still being measured. If too many moles of thiosulfate ions are used, then the concentrations of reactants for the main reaction change significantly before the colour change occurs. And this causes the rate of reaction between them to also change, meaning we are no longer measuring just that initial rate of reaction. To take this one step further, if we control the concentration of iodide ions as well, we can also investigate how the initial rate of reaction changes depending on the concentration of iodide ions. For example, imagine we carry out the iodine clock experiment using a concentration of iodide ions of 1 × 10⁻² mole per decimeter cubed, and the time it takes for the colour change to occur is 120 seconds. The rate, therefore, can be considered as 1/120. Remember, rates are per second, as in seconds to the -1, 1 divided by seconds. The process is repeated using a concentration of iodide ions of 1.5 × 10⁻² mole per decimeter cubed, this time given a time of colour change of 79 seconds, and a rate of 1/79. And then again using a concentration of iodide ions of 2 × 10⁻² mole per decimeter cubed, this time taking 61 seconds for the colour change to occur, given a rate of 1/61. From trial 1 to trial 2, the concentration of iodide ions has been increased by a factor of 1.5, as in the concentration of iodide ions used in trial 2 is 1.5 times greater than the concentration used in trial 1. The rate has increased by a factor of pretty much 1.5 as well, as 120 divided by 79 equals 1.51. Equally, from trial 1 to trial 3, the concentration of iodide ions has been increased by a factor of 2. The concentration of iodide ions in trial 3 is twice the concentration used in trial 1. Again, the rate of the reaction has pretty much doubled, the reaction has happened twice as fast. This tells us that the rate of reaction between iodide ions and hydrogen peroxide molecules is first order with respect to iodide ions. If you're unsure about what that means, orders of reaction have been covered in a separate video. Check the links in the description below. So, to summarize, clock reactions can be used to investigate initial rates of reaction. The iodine clock experiment can be used to measure the initial rate of the reaction between iodide ions and hydrogen peroxide. When reacted together, iodide ions and hydrogen peroxide form molecules of iodine, I2. Starch indicator is added to the reaction mixture, and this changes colour to dark blue-black as soon as iodine gets formed. To delay the colour change and measure the time taken for a known number of moles of iodine to be produced, thiosulfate ions are added to the reaction mixture. The added thiosulfate ions react with iodine molecules as soon as they are produced from the reaction between the iodide ions and hydrogen peroxide, forming iodide ions again. This means the colour change of the starch indicator is delayed until all the thiosulfate ions have reacted with any iodine formed. As soon as the thiosulfate ions have been used up, any further iodine molecules produced by the main reaction cause the starch indicator to change colour. The moles of thiosulfate ions present at the start can be used to determine the moles of iodine that must have been formed before the colour change occurs. As thiosulfate ions react with iodine in a 2:1 ratio, the moles of iodine formed before the colour change occurred is half the moles of thiosulfate ions present at the start. By using this change in moles and measuring the time taken for the colour change to occur, we can determine the initial rate of the reaction. Change in concentration divided by change in time. The moles of thiosulfate ions at the start must be very small compared to the moles of hydrogen peroxide and iodide ions. This means any change in the concentration of hydrogen peroxide and iodide before the colour change occurs is very, very small, and as a result, the rate of reaction doesn't change very much, and it is still the initial rate of reaction that's being measured. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.